Okay. So thanks so much, everybody, for joining. This is the, I guess, speaking and/or ambiguously research component of the qualifying exam for Arun for the PhD. So he's going to give us about a 40-minute talk.
Yep, about that.
On work he's done so far, and then some directions for future work based on this. And I think during the talk, just keep it to very short, clarifying questions. We'll have time for an extended Q&A at the end. I think we'll go with the committee first.
Yeah.
Make sure everyone's satisfied. I think open it up to everybody else for any questions you still have.
Great.
All right.
Awesome. Yeah. Thank you for the intro, Zach, and thank you everyone for coming. Today, I'm going to be talking about leveraging parallelism to accelerate quadratic program solvers for MPC. So to jump right in, a quadratic program is a minimization problem where you have a vector of decision variables. In this case, I'm going to denote it as y, and you're trying to minimize it subject to certain costs and constraints. And in particular, when you're dealing with QPs, the cost will have this sort of form where the landscape is a bowl. So here I'm showing a 2D example where the height is the cost. And in this talk, I'm going to assume strong convexity just to make things a little simpler, but we can discuss, some of the details there. And then in addition, you'll have these linear inequality or equality constraints. So that divides the landscape into a feasible and infeasible region. And you can think of the constraint boundary as being, in this case, at the line, but in higher dimensions, it would be a hyperplane. And then the feasible region is like a half space in your area. So why do we care about QPs? One of the main reasons is that a lot of problems in robotics can be solved either using QPs or using QPs as part of the process. So things like task space inverse kinematics, planning problems, state estimation like batch linear least squares. And then what I am really interested in is control problems. So a very common example of this is solving, for example, the soft rocket landing. And that's using model predictive control. So model predictive control is a particular control strategy where you're solving for a state, a trajectory of future states and controls that obeys the dynamics, the model of your system, the physics, minimizes some sort of cost. So that might be something like, fuel consumption or tracking a reference, and then also obeys any additional system constraints. So in the case of the rocket landing, those constraints could be things like don't go through the ground, obey the thrust cone, stuff like that. And then the general strategy with these MPC problems is that you want to solve the problem, apply the first control from that future state on the robot, get the new state, and this will include, anything that comes up because of model mismatch or perturbation mismatch or perturbations or disturbances, and then you resolve the problem, and you do this over and over again. And a really common example of doing this with nonlinear model predictive control and sequential quadratic programming is the biped robot Atlas from Boston Dynamics. So here you see a GIF of it doing parkour, where that set of blue arrows is this future trajectory that's being planned over and optimized over. And this problem, you can pretty much express every time step by linearizing everything and turning it into the QP form. And this is kind of an existence proof that we can do whole body really fast MPC using QPs. We know not many details of what BD is doing here, but we know that they spent a lot of time to really specialize their model, specialize their solver, and they're using a lot of tricks to make this work. The big thing is, though, we want to be able to generalize this. We want to use it on more systems, hopefully open it up and make it possible for us to do this. And some of the main challenges that running MPC in real time adds to our solvers is that these solvers need to be able to solve the same problem or similar problems 50 to 1,000 times a second. And every time you solve the problem and apply the control, your constraints change a little, your states change a little. And so you need to cheaply be able to update the problem. And then once you've updated it, you want to be able to converge very quickly to a coarse solution. And the way to think about this and why we don't care about super fine grain accuracy is first, the longer you spend, the more latency you're adding, the less responsive your controller is going to be. And also there's always going to be errors in the model and stuff like that. So there's a point of like diminishing returns where you want to be able to get to something really fast, apply that, get the new state, and just go as quickly as you can. And then in order to do that, we can observe that the problem, these blue arrows, is not changing significantly time step to time step. And so we want to use previous solutions to be able to warm sort the problem and use it as an initial guess instead of solving from scratch every time. So this is challenging. This is like a challenging set of requirements to meet. And oftentimes when we're doing this, we have to use simplifications to achieve real-time performance. So a common example of this is to use a reduced order model. So in Quadrupeds, which is a system I work on a lot, we use a single rigid body with point feet and ground reaction forces. And this makes the system a little less nonlinear and makes things easier to solve. But then if we do decide we want to use all the model information we have, oftentimes we end up having to go to a hierarchical control structure where we accept that the MPC won't run as quickly. It might run 20 to 100 hertz, but then you may have this low-level PD controller or something like that to catch disturbances and noise and pretty much act like a low-pass filter to compensate for the fact that you're not running things as quickly. And this works great in a lot of cases, but obviously there are limitations. In the case of reduced order models, it's harder to reason about joint limits and torque limits. You also have limited inertia reasoning. So this doesn't matter, for trotting, but if you're doing balancing or you're trying to right yourself in the air, that's when you might want to care about what the legs are doing. And then the big thing I care about is it's hard to reason about contact. So if you want to use your knees, your shins, your elbows and stuff like that, and that's not in your reduced model, you're going to have to do a lot of things to be able to reason about that. And then even if you go to the hierarchical control, because you have this bi-level structure, you end up having to use a more conservative controller because you have this underlying controller that may not be able to reason about the limits that your MPC controller can reason about. And so you need to give it a little bit of leeway to make sure that if you have something that goes right at the limits in MPC, that the PD controller won't push it past that. And then also, because you're running MPC slower, you're also going to be less robust. So there's going to be a certain level of disturbance, certain types of high frequency dynamics, stuff like that, that you won't be able to correct for as quickly. So while this works in a lot of cases, our goal is we want to be able to use the model information we have. We want to be able to use everything we know and solve these more complex problems with more complex systems, just like Atlas. One of the main challenges is that in the past, some of this would have just been taken care of for us with the advent of faster and faster compute. But unfortunately, in the last couple decades, we've seen a real reduction in single core clock speeds, and they're not advancing as quickly. Whereas on the other side, we have the parallel compute, which is most of our compute gains are coming from that. So in GPUs and CPUs like the Threadrippers. And RL and ML techniques have really been able to leverage that and have been able to use the parallelism both on the GPU for training and then on the CPU for deployment. But it turns out that a lot of QP algorithms that we use end up having a primarily serial component. And we want to figure out, and that kind of gets dampened by this dampening growth curve. And we want to figure out how to use the parallel compute. So to understand that problem a little bit better, I'm going to walk you through a QP, one of the ways to solve a QP, and show you where that problem comes from. And to do that, I'm going to talk about the alternating direction method of multipliers, which is a method used by the operating splitting QP or OSQP solver, which is very common in robotics and is known to be pretty robust. And so the way ADMM works is you first start by introducing a splitting variable in your problem. And that splitting variable is now going to be equal to the constraints, the GY term. And so now you have an equality constrained problem. And then you're also adding an indicator function in to the cost that is 0 if z is feasible, so greater than or equal to 0, and infinity if z is infeasible. And at first, it must be a little counterintuitive because one, I've made the problem larger, there are more variables, the cost is no longer quadratic, it has a discontinuous term, why would we want to do this? And it turns out that this actually helps us decouple the problem and make it much easier to solve. So to see that, we can look at the augmented Lagrangian for this problem. So the augmented Lagrangian has three terms. It has the cost term from before. It has this Lagrange multiplier term, which prevents you from violating certain constraints, and where gamma here is a Lagrange multiplier. And then we have a penalty term that is trying to keep G, Y, and Z close to each other. And at convergence, you want that term to go to 0, get very close to 0. This is a little bit bulky to carry around and do math with. So to simplify things a little, I'm going to combine the Lagrange multiplier and penalty terms. And the way I'm going to do that is I'm going to first add a gamma squared term to the end, which won't change the problem if you're just minimizing over Y and Z. But it does let me pull out this rho over 2 term. And then you can see in the parentheses, we have a nice quadratic. So I can simplify that and collapse it to get this. And you can see that the gamma has now been absorbed into the penalty term. And then finally, with a change of variables, I can define a new scaled multiplier, lambda, that I can use here. And this is kind of called the scaled form of AL, and it's a little bit easier to work with and simplifies the math a bit. So now that we have this Lagrangian, how do we solve the problem? OSQP since it's using ADMM, we end up doing a similar thing with AL where you minimize over the primals and then you do a dual update step. But in this case, we're going to alternate minimizations between Y and Z before doing the dual update. And the reason for this is it turns out these problems in Y and Z are very simple to solve. So if you look at, for example, the Lagrangian and only determine the only parts that include Y, you can see that this is just a simple quadratic. And we know how to solve that. We can take the gradient that gives us a linear system, and then we get the following update. And just for some terminology, the matrix we're inverting, we usually refer to as the Kurushkin-Tucker or KKT system. And then the rest of it we'll refer to as the right-hand side for the rest of this talk. And then if we look at the terms that depends on Z, you have this indicator function as before, and you just have the penalty term. And this is a little tricky to work with because, again, that indicator function is discontinuous. But because we know we're minimizing, we can turn this back into an inequality constrained minimization. And now, if we look at this, this is just a decoupled least squares problem in Z, where if there's no constraint, Z would just equal gy plus lambda. And then because we have the constraint, this ends up just being a projection where we take the gy plus lambda and any term that is negative, we clamp to 0. So again, that's a very simple step to compute. And then finally, to understand where the dual variable update comes from, we can look at the stationarity condition or the gradient of Lagrangian with respect to Y. And you can see that we have a constraint violation term and this Lagrange multiplier estimate that kind of show up in the same place. And pretty much at convergence, right, we want this constraint violation to go to 0, but we want the lambda to capture it in such a way to prevent you from going into the infeasible region. And the way we do that is using penalty offloading. So at every iteration, we capture what the current constraint violation is and bake it into Lagrange multipliers. This is one way to see this, but there's another way where if you write down the dual problem to this, this ends up looking like a gradient ascent step on that dual problem. So now we have our 3 steps. We do our linear system, we do a projection, and then we do a dual update. And ADMM, the OSQP solver, pretty much iterates these steps over and over again until you meet some sort of convergence criterion. And it turns out that there's like a good history and a lot of research behind this converging very quickly to coarse tolerances and behaving quite nicely. Just to talk a second about the computational cost here. The linear system solve is going to scale cubically with the size of the matrix because you have an inverse. And then for the projection, we have a matrix vector product, which scales quadratically. And then finally, we can reuse that matrix vector product in the dual update. So that's just linear. And clearly, the linear system is the thing that will dominate the speed of our solver. However, what you can notice is that this linear system only changes, the KKT system only changes when the penalty term changes. And in ADMM, unlike AL, your goal is to use the penalty to balance the constraint violation and the cost convergence. So if rho is large, the G transpose G term dominates and you're minimizing the constraint violation. And if rho is small, the H term dominates and you're minimizing and you're making progress on the cost. And it turns out that you don't have to change that penalty very often. So the way OSQP does this very quickly is it leverages that fact to do some extra work and kind of amortize the cubic cost over multiple iterations. So to understand that, if we look at the linear system we're solving, and I'm just going to use B to represent the right-hand side, and that's going to be the thing that's changing every iteration, but our linear system is going to say the same for a certain number of iterations. We can take advantage of the fact that by construction, this system is symmetric positive definite. And so that means we can do a Cholesky factorization, and we can, to break it into a lower triangle and upper triangle, lower triangular and upper triangular multiplied by its self-transpose. And in particular, oftentimes this has a sparsity structure that looks like this. So we get these nice sparse lower triangular matrices. And then we can break this into 2 easier problems. So a backward substitution to get this intermediate variable V, and then a forward substitution to solve for Y. And to understand why this is simpler, we can look at a simple 3x3 example. So here, if we just look at these equations, right, it's immediately apparent that you can solve for V3 very easily by doing this. And then you can plug that into the equation above it to get this. And then you can plug that into the equation above it to get this. And again, this is the backward substitution, right? We're moving from the bottom of the matrix up and solving these much smaller problems now that we have the factorization. And it turns out because we're solving these problems with sparsity and things like that, this ends up being much closer to a matrix vector product in terms of the computational costs than scaling cubically. However, the big issue here is that with the factorization backsolve, which is used to solve a lot of linear systems, is that this is inherently a serial process, right? We have to do each of these steps in order, and it's not clear how you would map this to a parallel system. That's not immediately apparent. So that brings us to my work, which is ReLU-QP, a GPU-accelerated quadratic programming solver for model predictive control. And this is work that I'm going to be presenting at ICRA in May. And so the goal here is we want to parallelize ADMM, and we want to parallelize our solver. And in order to kind of understand how to do that, we need to understand what are the key parallelizable operations, what makes it easy to parallelize something. And to understand that, we can look at what the classic neural network operations are that ML uses to really leverage parallel compute. And there's two kind of big ones. The first is just doing matrix vector products, which you can parallelize as vector-vector products very easily. And then the other is these nonlinear activation functions. So this is where you're applying an element-wise nonlinear function to each element. And again, because it's element-wise, you can parallelize this very easily. And in particular, one activation that's used often is the rectified-linear unit, or ReLU, which is where we got the name. And that just looks exactly like the clamping operation. So if the input is negative, it becomes 0. And if the input is positive, it doesn't change. So if we put that to the side, and we look at the ADMM iterations, I'm going to show how we reorganize them to fit into these parallelizable operations. So the first step we did was we moved the lambda update to the beginning of the order. And this doesn't change anything about convergence because we initialized the problem to have gy equal to z. So for the first iteration, the lambda update doesn't do anything. And the steps are still happening in the same order. We're just grouping them differently. And we're grouping them so that the nonlinear function is the last thing that happens, similar to a network layer. And then our next step is we're going to do some offline compute by computing directly the inverses of this KKT system. And you can think of this as being similar to computing your weights and biases, your training step. This is your offline step that you're going to do to make the problem easier to parallelize online. And then once we've done that, we can expand all of this. And I'm going to add an additional variable just to show how the nonlinear piece comes out. And I've colored all the variables we're interested in here to see that this is just a bunch of matrix vector products, right? So you can imagine taking the lambda update and plugging it into the y update and expanding and simplifying, and then taking the lambda and y updates and plugging them into the last line and expanding and simplifying. And you get something that looks like a very big matrix vector product with a bunch of terms in it, which means you can write it like this, where we have now this weight and bias terms that are pretty much conditioned on the penalty and change based on the inverse of the system. And clearly now these map pretty much directly to this ReLU affine layer. And this is a fully parallel iteration. So once you've done the pre-compute on the inverse, you can easily parallelize this. And the rest of the ReLU-QP algorithm is just stacking this up. So now we look like a fixed point iteration on a deep weight type network. And then we're just occasionally changing what W and B is using, we pretty much compute a bunch of inverses with a geometrically scaled penalty, and we can swap those in and out occasionally if we need to improve the convergence of the algorithm. But that's the main way we parallelized it. So how does this work? How is this actually better? So the first thing we did was threw a bunch of dense quadratic programs at it. So these programs were between 10 decision variables up to 2,000 decision variables. And we compared it to two solvers, OSQP, the one that this algorithm is derived from, and then ProxQP, which uses a proximal point algorithm, which has some different properties. And you notice that here we're just solving to coarse tolerance. That means that we are trying to drive the constraint violation and the stationarity condition to 10 to the negative third. Because we know that ADMM works really converges very quickly to coarse tolerance. And you notice that ReLU-QP starts winning at around 200 decision variables and then is 40 times faster when we get up to 2,000 decision variables, which is fantastic. And it turns out that even if you go to tighter tolerances like 10 to the negative 6, we're still winning by a factor of 30. So this is great, but this is not the actual use case, right? These are dense problems. They don't have the sparsity, the swarm starting. This is an example of what the solver can do, but we really need to throw real MPC problems at this to see is this actually what happens in practice. And so to do that, let's look at what a classical QP MPC problem looks like. We have one here where you have this LQR cost on your states and controls. And then you have an additional dynamics constraint, which is linear or from some linearization with some initial condition. And then you have some, state and control constraints. So this might be your joint limits at each time step or your torque limits at each time step. And it turns out you can directly transcribe this into the problem that we saw earlier by stacking up all the states and controls into one big vector y. And then you have this very sparse Hessian that looks like this with the block diagonal cost terms on it. And then you also have the constraint matrix. I'm just showing it for the dynamics here, which has this Markovian temporal structure that links the states together. However, the main issue here is that this is very sparse, right? And as we talked about, when you have a very sparse system, sparse linear solvers on the CPU are really good. And on the GPU, especially because we're doing an inverse, which results in fill-in and things like that, that math will not be as nice. It'll be dense, pretty much it's unlikely that we would win with this. And it turns out that in practice, you don't. So what we need to do is we need to figure out how to turn this into a dense system that is better fit for the dense matrix vector products. And the way we did this is with condensing. So pretty much to turn this from a direct problem where you're solving for states and controls into an indirect problem where you're doing single shooting and you're writing all the states as just a function of the initial condition and all the controls up to that time step. And so if you can get that by just plugging in and iterating on the dynamics constraint that you have, so you can write everything in terms of the controls, and now the decision variables are all just controls with no states. And you can do this transformation of the problem. However, there's a big issue here, and that issue is that if there's any unstable modes in your state transition matrix, which is the A matrix here, this is going to get, as the horizon goes farther and farther, the conditioning is going to be terrible, the eigenspectrum is terrible, the numerical properties of this is just bad. And that's why usually we try to avoid doing this. However, there's a really simple solution, and that is to bake in a stabilizing state feedback controller. So instead, now we're writing our control variables as deviations on that policy. And by baking it in, we've now changed our dynamics from open loop to closed loop dynamics, where we're assuming a known policy. And as long as this policy is truly stabilizing, the eigenspectrum of these matrices' powers will not explode, and you'll have really nice properties. And you can pick any K matrix here as long as it's stabilizing, but in particular, because of the structure of the problem we're solving, we use the infinite horizon LQR gain to initialize this system. And what that means is that if no constraints are active during your trajectory, the deviations are just zero. And then your solver is really only reasoning about what happens when the constraints like torque limits and stuff become active in your problem. And it turns out that when you plug this in, because now all the future states rely on all the previous controls, it makes everything nice and dense. And in addition, it turns out the dynamics constraints are implicit in the single shooting method. So G just includes the state and control constraints like the torque limits and stuff like that. So to test this, we threw this at a bunch of random linear systems with control dimensions from 10 to 50 and 40 knot points. And the goal here is just to drive the system to the origin where we've made sure we're starting far enough away that the constraints are actually active and the solution isn't just automatically zero. And you can see that ReLU-QP is winning at pretty much every size and is up to 10 times faster for when we get up to 50 controls. But again, this is just a random system. And let's get to the real thing. Let's get to actual whole body control. And so to do that, we just tossed it on a whole body atlas model where we're balancing on one foot subject to getting pushed. And you can see that from this trajectory, we have, all 58 states and controls. We're using the arms, we're using the inertias, we have the torque constraints in, and we're solving for 3 different horizons, 30, 40, and 50 knot points. So between 0.3 and 0.5 seconds. And this corresponds to really big problems with about 900 to 1,500 decision variables and constraints. So how does ReLU-QP do? Well, it turns out it pretty much blows OSQP and ProxQP out of the water. It is able to solve at 2.6 kilohertz when you have 0.3 seconds trajectory as opposed to 200 hertz for OSQP. And it's 20 times faster when you have a 0.5 second trajectory and you have 50 knot points. So this was really encouraging, but let's make it even harder. Let's throw this at a quadruped with an arm where it's reaching over. It's really far from its linearization point. It's picking something up and it's trying to drive it back to zero. And here we have 52 states and 32 controls because we've now added all of the contact forces as well. We have a linearized friction foot cone constraint. We have pin foot constraints. We have torque constraints. And this ends up with around 1,000 decision variables and about 1,500 constraints. And again, we're able to do a lot better than OSQP, up to 2.6 times faster. And surprisingly, ProxQP, even when you gave it a lot of iterations, was not able to stabilize the system. I think one of the reasons for that is we are very far from the linearization point and the conditioning is not great. So that might be one reason why I was struggling to stabilize. And then in addition, you notice the speed here is definitely a great gain because we're getting close to the limits on actual hardware of how quickly you can send torque controls over the communications they give us. But it's not like it's not 20x like Atlas. And we think one reason for that is that, one, we have the force constraints that we're not doing this feedback trick on, so there's some sparsity in the problem. And two, if we look back at like the weight and bias matrices, they scale, Y just scales with the decision variables, but Z and lambda scales with the constraints. So that problem gets much faster with faster with the constraints than with the decision variables. And finally, we did have to use more iterations to make sure that this could actually stabilize the system. So this is we think this is really cool, but there are definitely some limitations of this. So one of the big ones is that there's this decent amount of overhead for doing all this pre-compute. So for Atlas, computing all those inverses and assembling the layers took about 12 seconds. And for the Quadruped, it took 7 seconds. Now that's nothing like compared to training, but if you're doing a factorization, this would definitely be slower. And then in terms of memory, Atlas used 14.4 gigabytes, which is close to the limits on on a good desktop card. So that's definitely a lot of memory that you're using, though I think you could get away with less. If you really tune the penalty parameters, you could probably get away with less. And then the big limitation is that because you're computing the inverses beforehand, you're restricted to a single linearization. So this is really great if you have large systems with fast dynamics where you can get away with one linearization, or if you don't care about the memory, maybe you can linearize at a bunch of different points and kind of have like a chart to cover your nonlinear manifold. But this is not the solution we want for running something on Atlas, let's say, or something where we do care about this and we want to do sequential quadratic programming, let's say, or something like that. So that was the main contribution, but we also tried a different method, which was an iterative method that would let us update these matrices online, and that's called conjugate gradient. And I'm going to go through this a little bit quickly, but pretty much the conjugate gradient algorithm is a way to solve this linear system or like minimization where you have a positive definite Hessian. And the way it works is it keeps track of 3 terms. So there's this residual term, which is the gradient you're trying to drive to 0. There's a search direction, which is the negative of that gradient. And then there's your current solution, y. And conjugate gradient does a loop because it's an iterative method. And in that loop, what it does is it solves a 1D minimization along the search direction, which you can express as matrix vector and dot product. And you don't need to invert a linear system to solve that. And then it just updates the current solution, the current guess, and the residual with that new thing. And then the key thing about conjugate gradient is that it's able to compute the new search direction, which has this conjugacy property, which essentially means that you can run all these 1D minimizations without them making the problem worse. You're guaranteed that they will all be minimizations separately. And the way I like to think about that is conjugacy is pretty much orthogonality in the eigenvector basis of the matrix. So if we have, for example, a 2D cost function like this, where the ellipses represent the level sets, you can imagine this algorithm is pretty much taking a step along the major axis and then along the minor axis to get there. Except the great thing is I don't need to compute an eigenvector decomposition, which is very expensive, right? I can do this much simpler operation to get my conjugate vectors and figure out what my steps are. So OSQP did this. And unfortunately, it turns out that with their system, they were only able to win once they got to 1 million decision variables and running at 10 hertz, which is, again, not the area that we're targeting. But it turns out that conjugate gradient is really sensitive to the eigenspectrum that you have. So if you have uniformly distributed eigenvalues, you may need as many iterations as the size of the matrix to converge. Whereas if you have clustered eigenvalues, because there's these symmetries and these subspaces, you can get there much faster. And one way to do this is with preconditioning. So OSQP was just doing like a kind of basic diagonal preconditioner, which wasn't super sophisticated. But we ended up working with people from Brian Plancher's group, so Emre Atabag and Maloney et al., on extending a work they did called MPC GPU with William Gerard, which pretty much built a very dialed PCG, preconditioned conjugate gradient solver that used a symmetric stair preconditioner, took advantage of the sparsity, did a ton of very fancy things with custom CUDA kernel to like really try to dial CG in. And to test this out, we pretty much did a Karate Kid kick on Atlas. So this fun maneuver that we knew would hit the dynamics constraints. And the key thing to know is because we're now updating the dynamics, every time we update the dynamics, OSQP has to refactorize the system, which is a serial operation. And we have to rebuild our preconditioner, but that's a parallel operation. So we were hoping that this would win, and it does, but not significantly. And I think one of the main reasons behind this is for every ADMM iteration, you're still doing multiple matrix vector products for each CG iteration has one of those. And when you're doing a backsolve, that also looks like matrix vector products. And there's this trade-off. It turns out that, sparse linear solvers on the CPU are really good to the point that when you have a bunch of these CG iterations, they end up kind of falling out in the wash. So ultimately, this is not the solution that we were hoping to get. And that kind of brings me to my future work. So I want to keep exploring this problem across multiple dimensions. So the first thing is to look at other methods, second order, first order, and sampling-based methods. And it seems to be the intuition is there's this trade-off where as you go to first order and sampling methods, you need more iterations per solve, but those iterations may be more parallelizable. And there's a kind of a trade-off there to explore. And then in particular, we want to explore this for different problem parameters. So like size and sparsity. So in Brian's work, they were able to get really big wins on MPC GPU because their problem size was perfect to pretty much fit with the hardware design that they were running on and fit within the memory and do all these very fancy tricks. But with the Atlas problem, the matrices were too large to do that, and that instantly added a ton of overhead and like hosed our convergence rates and made it tough. And so that's also the other dimension that we want to look at is like, how does this work across hardware, on the CPU parallelism with GPU parallelism for shared memory systems? Are there ways that we can leverage what CPUs are really strong at and what GPUs are really strong at in order to develop these faster, more general solvers that can leverage the parallelism? So with that, I'd like to thank everyone who helped me on this work, John, Swami, Kevin, of course, my advisor, Zach, and Amaran, Maloney, and Brian in Brian's lab, and open up the floor for questions.
All right, so I guess start with the committee and we'll arbitrarily give the floor to Larry. If that's okay, if you want to. Kevin's not on.
No problem.
We have Kevin. If we go by farthest in distance, it would be Kevin.
Whatever
But
you
he's
all
also
prefer.
much closer in spirit.
Okay.
To the last.
All right, so Larry, if you'd like
involved in
to.
that work, so.
Yeah.
I'll be happy to.
Yeah.
I enjoyed this very much. Thank you for inviting me, Arun, and especially it was really, I was thinking about a number of things behind your problem, and as the presentation evolved, you seem to kind of addressed all of these things as you went forward. So I was very glad to see this. Let me ask a couple of simple questions. In slide 4, I'm not sure I understand the typo or whatever, but it looked like you were saying that H was semi-definite.
Oh, yes, sorry, that is a typo. I think I just slipped out.
Thank you.
And we actually can deal with semi-definite. So like the actual details, we had a regularizer, there's a damping term, like.
Well, I
But
mean, the way you're using ADMM, it can be semi-definite as long as it's in the range space. of
Yes.
the Constraints, right?
Yeah.
Which I was just wondering, well, more than that, will this always be positive definite? And if not, what do you want to do? I mean, you're gonna have to regularize it or what?
yeah, so there's a couple differences. If I actually go all the way to like the ADMM, this, where is the KKT system? This KKT system, right? So if H is positive definite, right, by construction, this whole thing will be positive definite. If it's not, the way that we currently handle it is we add a very small regularizer. But I don't know if you always have to, depending on pretty much like where your initial guess is and where your solution is and like the subspace you're working in. Like for example, when we construct MPC problems, sometimes we'll let Q be semi-positive, semi-definite, and then but we'll have R be positive definite, and the constraints pretty much tie the two things together, so you don't need H to be strictly positive definite because the constraints will add that and make this whole thing positive definite.
Okay, good. Okay, slide 13. This was kind of interesting because you're using ADMM, and one of the things I'm really curious about with ADMM, and this basically goes back to the theory of augmented Lagrangians, which is rho. Okay,
Yes.
and I'm just curious, in your experiments, how often did you actually have to adjust rho?
So very little. I was actually surprised by this. It turns out, for example, the Atlas example, we made this easy for OSQP because it never had to change row. It never had to refactorize. We were still able to win. It pretty much seems like you can run a couple experiments to figure out what row should be. And then you can lock that. And I find it's not as fast in practice than if you can update row. And for us, we can kind of do it for free, but like it's very small difference and it's unclear.
Well, how can you do it for free?
Oh, because once we've computed all the inverses beforehand, then we can just switch the rows in and out, right?
Okay, so that's what you
You do that for like a fixed.
Yeah, it's pretty much a geometrically scaled. It's very similar to like the scaling that OSQP uses, because OSQP has to decide, do I want to spend the time factorizing? So it has this thing where like it only does it when the penalty's changed by a certain amount.
Okay, that's clever. Yeah,
Yeah.
okay.
Whereas we can do it like way faster.
Yeah, because I think that's one thing. I mean, I think it's the case where G is still conditioned,
Yeah.
starts to get rank efficient, but rho starts to blow up.
Yeah, because you do have that like G transpose G term
Yeah.
that squares the eigenvalues, and that can become ill conditioned, and you'll have problems there.
Does that ever happen to you?
So there's additional stuff like matrix equilibration that we do to the problem in the beginning to make sure that doesn't happen. And then we also, by adding that stabilization term, that also kind of prevents it from happening. And so that makes the problem better conditioned.
One thing, I mean, this was just kind of a side note, but I don't think it's really relevant anymore. If you did an eigenvalue decomposition on this KKT matrix that you have in yellow, then it would be fairly easy to update rho on the fly.
So we looked into this.
Okay. Yeah.
I think there should be, I agree with you. I think there should be a way to do this. I can't remember. I think there's a reason we didn't
You
finish
have
that
these
exploration.
other
but-
ones, the eigenvectors.
Yeah,
And then you're just dividing through by, some factor that includes rho.
yeah.
And you pre-compute all the eigenvectors.
Yeah, I think, so we did do this. I think it turns out because, unless I'm misunderstanding you, because you now have to do 3 matrix vector products for like the eigenvector basis, the eigenvalues, and then the transpose the eigenvector basis, that it ended up being slower and taking more computation than to just use the inverse.
I just thought about it. I don't know how much of that you can do up front.
Yeah, but we were also thinking there might be a way to figure out like what is the ideal row, and we looked into that using some like monotone operator theory with like the clamping step. But that was a little beyond my current like mathematical knowledge.
Okay.
But there might be something you could do there as well to like figure out the ideal penalty given some problem.
This is great. Maybe the last thing, and I should really not spend too much more time, but I think the thing about preconditioned CG,
Yes.
is that something that you're focusing on? Is that something that you've just taken off the shelf, or is that something that you think is worth going deeper into, or just maybe a nice to have?
Yeah, so we were mainly like using something that had been developed by Brian's lab and like wrapping it in ADMM steps and seeing what we could do to make that work. And from our experiments, it seems like you can maybe get a win, but it's not big enough that it's really worth putting the time in to get it, unfortunately. Yeah.
Is there anything you can do with classical sparse matrix composition? Because a lot of the work, the analysis phase where you're pivoting, that can all be done offline.
Yeah.
And then you basically end up with factorizations and backsolve that are linear in the number of non-zeros.
But serial, right?
Yeah, but
Yeah.
serial, of
Yeah.
course. I don't know if you can do anything more than that. Yeah.
Yeah, that's I really don't, it's hard to figure out how to parallelize that and use that because you're still solving linear system with the backsolve method, and that just.
There are parallel solvers in HSL.
Okay.
I don't know.
Do they do like
They're
some
doing-
block something?
Sorry?
Or are they using like some block structure or something to do that? Yeah.
Doing some kind of block
Yeah.
procedures, something like that, but I don't know how they work. Or, sorry, some of these are frontal methods.
Yeah.
Okay.
Yeah.
I don't think I'm familiar with
The
frontal
frontal
methods.
stuff, which we looked at a bit, and Brian
Mm,
Jackson, whose committee you're on, he actually went pretty deep on that stuff, and
okay, did it help?
He spent the better part of a year, taking that stuff, and it just, he beat all of the commercially available multi-crumple solvers. So that was an accomplishment, and it was still slower than QDLDL on a fast single thread.
Yeah.
Machine.
Yeah, that's the thing. It's like I'm definitely criticizing CPUs here a little bit, but like they are still like beating a serial linear solver is hard.
Yeah.
But, yeah.
Very good. Thank you very much. I really enjoyed this.
Thank you for coming.
Yeah, well, I mean, as Larry said, I had a lot of questions that you then answered before we got to the end of your talk, and then Larry asked a bunch of the other questions. So that's the advantage of it first. This is like a small thing, but if you go back to 33, I mean, I understood like at a high level what you were doing here, but then
Yeah, so you're talking about like the plugging in up here?
I was looking at the yellow. I want to see a W on the left, but then W never gets used again.
Oh, it's here. Yeah, sorry. I should have made that clearer. I just wanted to really like make it obvious how this nonlinear activation comes out. And how you can make it into this matrix vector product and then a clamp. But yeah, that's where.
So basically, so this is like the fourth equation that
Yeah, I pretty much am just dividing this into two steps.
Got it. Yeah, and you just went by quickly, and I was like, wait, what's W?
Yeah, sorry.
Yeah, so the you know, I was thinking about this as like you said, oh, the problem is that this part is serial.
Yeah.
And is it, and then you were trying to make that part parallelizable. Is there a way to sort of parallelize at a different level?
A different level. Yeah.
So the example I was thinking of is we did something where we did a parallelized line search.
Okay.
In ILQRs, and then we're like, the shooting could be linear, but then we like, you know, rather than trying one next step, we tried like 10 next steps all at once, right? Or I don't know, how did you sort of settle on like, here's where we want to parallelize
This actually reminds me, because for the CG, the one time that might win, like for in Brian's case, is if you can do everything on the GPU and then do the line search on the GPU, that can be better than doing things on the CPU, even if it's not. Like those can all add up. And it's a good question, pretty much where you draw this line between like the offline and online compute. And we pretty much like, there was this nice nugget that we wanted to explore, but that's another one of the dimensions that I want to look at in terms of, you know, what works well. I'm sure for different problem structures and stuff, that's going to matter. Like if your line search, if you end up backtracking a lot, then that's really important. But if your line search doesn't end up being that active, then is that going to win you much? So yeah, that's a good question for sure.
And then another question on this slide, it seemed like, so you say that just pre-computing this H matrix, is that what did most of the work? Or you then went through all this other stuff?
Yeah.
But you know, the previous couple slides earlier, you said, oh, the problem is this matrix inverse is the O of n cubed thing.
Yeah.
And that's what, and then it's like hard to parallelize that part. But then you got here and you said, oh, and we just pre-computed that anyway. So if you just pre-compute that, you don't have any O of n cubed.
Yeah, so by pre-computing this, it's similar to factorization, right? Like where you can amortize and then it becomes a bit matrix vector product. And so this is doing most of the work. The big difference is like OSQP could pre-factorize everything, but then it would still need to do the serial backsolve. Whereas here with the inverse, we can get around that. And that lets us like, so yeah, the inverse is the main thing here where you can just, once you've done that, you can turn this all into a nice.
This question. So here's, what's the big O, what is the online iteration cost of this thing?
Oh, O of n squared, yeah.
Is it n squared? If you have infinite cores.
Oh, yes, so parallel that it's linear. Yeah, it scales linearly with the size of the system. Yeah.
I don't know, have you done it like an ablation study to tell like, how much of your speed up is coming from pre-computing this matrix inverse versus this fixing the serialized?
So I think we've got at that indirectly when we were doing the Atlas thing and not having OSQP prefactorize. So then the prefactorization was out of everything and the inverse was out and like both that. And then it was just the matrix vector products, the serial version, like the backsolve and the parallel. And we were still winning by a decent amount. But I do think like we could look into that more. The main, like one issue we did notice is like this system is still pretty big compared to like the OSQP, the small backsolves. And so that does slow things down.
This is a really good question that we should make sure we drive home this point.
Yeah.
That you're being like apples to apples fair.
Yeah.
You could run the exact same thing on a CPU core, right? Versus
Yeah.
on the, and that would tease out exactly. what
Yes,
you're doing.
yeah.
I think it's-
That would be actually, yeah, a good test to do is like run this all on the CPU. Well, mixed because the CPU has so few cores compared to a GPU that like that thing might end up be the thing that dominates, where you can't.
Why do it single thread?
Yeah, do it. on
Oh, do it
single
single thread,
thread,
yeah.
just to point out like, hey, it scales like n squared if it's on a single core.
Yeah.
Yeah,
But if we can throw this on 10,000 cores, now it's.
Gotcha,
quarter,
yeah,
right?
yeah.
As long as we
Yeah,
have
that makes
exact
sense.
number of cores.
yeah, that
Which
makes sense.
I think is an excellent point. I think.
Yeah,
Yeah, I mean, it's kind of, you know, anytime someone's like, oh, you know, we made these 10 changes and look, it's better. It's like, and then you know, it's like, well, you know, did this change help? Did this change? Or is it
Yeah,
one
that's a
where
good
it's like, oh,
point.
Yeah, if you just did that, that's kind of most of it. The rest of it's just you spinning the wheels and stuff. That's fine. And then like when you run it, like you can run the combined thing. It's fine.
Yeah.
I guess last question, the first like kicking the atlas, the video and the quadruped you had,
Mhm.
those are both linearized around a single position.
Yes,
And you're still able to get this like angular momentum, like swinging your arms kind of stuff.
yes.
That seems, I don't know, that's kind of surprising. Is that because it's?
Yeah.
More to come on this.
Yes.
We're gonna poke at how far we can take that.
Mm.
Like, I'm sure once you go on a hardware with more of a model mismatch, that's tough. But I think, and Zach and I were talking about this, the intuition might be that as long as like your signs are right and your torques are pointing in the right direction, that you might be able to get pretty far with just that single linearization.
And then because it's a receding horizon NPC.
Yeah, you can kind of catch like all the issues that show up.
All right.
Yeah.
Interesting.
Okay, Kevin, I think you're up.
Cool. Hey, really awesome talk. I really only have one question, and that is when you show the example of the quadruped with the arm on top, you mentioned that you thought that ProxQP failed because the conditioning was poor due to how far it was from the linearization point.
Yeah.
Can you speak as to why being further away from that point would worsen the conditioning?
So yeah, I guess that's a bit of a misstep. It's less the conditioning. Though I do think the conditioning of that linearization is already not good in general. The bigger thing is the farther you are away, your linearization is pretty far. So any errors you have in your control, like the nonlinear model and the linear model are going to have more mismatch when you're farther away. So any small inaccuracies in your solution are going to be kind of made bigger by that fact that you're farther away and your gradients are not aligned and stuff like that. So you're right, it's less of a conditioning issue, and more, it seems like ProxQP, because it's solving the problem differently, it wasn't able to get to the accuracy that was needed to like make sure you could stabilize the system.
I see. I'd be really curious if you did like an ablation study on that and just removed constraints, if you could see what is really giving ProxQP so much trouble.
Yeah. Yeah, I definitely think that's interesting. We were kind of surprised by this, and it wasn't like the main point of that experiment, which is why I don't think we dug super deep into it. But like even if we like gave ProxQP a ton of extra iterations and made it, you know, converge much tighter than OSQP and ReLU-QP, it still was struggling.
Interesting.
Yeah.
All right. That's all I have, Arun. Awesome job. Thank you.
Okay, Zach.
All right, thanks. Yeah, obviously, I've not noticed that. I want to poke at something a little bit
Yes.
here that might be a little bit mean. So I don't
Okay.
want to push it too hard.
Go for it.
But you made me think of it earlier.
Yeah.
What happens in this, and I think it's important, like
Yeah.
in a lot of these MPC kind of context, what happens in ReLU-QP if you handed an infeasible problem instance?
An infeasible problem instance.
Which is very easy to do, right?
Yes.
In MPC
Yes.
situation.
When you could.
So I'm kind of curious, and we didn't really look at this,
Yeah.
so this is like a little bit mean.
Yeah.
But it's like on.
So I'm not fully versed, but I know that there's pretty much, it'll converge to an answer, I believe, that you can use to detect the infeasibility. Because there's a certain like primal and dual infeasibility conditions that you can check. So it'll converge to something, but it won't be a proper solution.
I think
like-
it's actually a pretty well-defined thing that should happen. If you go back to the ADMM stuff, but we haven't poked at this. Can we
Okay.
go back to the ADMM
Yeah.
equations?
The update
I
steps?
think this is, yeah, like, I guess what I'm getting at here is I think we want this thing to somehow
Yeah.
fail gracefully.
Yeah, like
in,
this.
like, nasty situations, and the ProxQP people, I know this because I just. They made a big deal about this kind of
Yeah.
infeasibility failure mode in their
Yeah.
solver, in their paper. And, keep going to where you write out like the ADMM stuff originally, like what happens, basically, like, you forget about the multiplier updates for a second,
Mhm.
like what should happen in an infeasible file, for instance.
You should have like G, Y, and Z not be able to line up with each other.
Yeah, so what will the thing converge to then?
Well, I guess because we're doing the projection on like the separate dimensions, it should be feasible in some and infeasible in others.
Yeah, I mean,
and-
just in some meta sense though, right?
Yeah.
It's basically just a penalty method at that point.
Yeah.
So it should kind of converge to something that's like a least squares.
Yeah, the
So-
closest, yeah, like a pseudo inversey type solution where you're getting as close as you can
Something.
without satisfying.
Yeah, some like basically weighted least squares.
Yeah.
Thing.
Which I guess is if you are only like slightly infeasible, that might be nice because it might be very close to the actual
Yeah,
solution
that's
if
what I'm
you
getting at.
fixed it. Yeah,
We should probe this.
yeah, whether it fails gracefully if that
What happens?
linearization's bad.
Because, well, do you know how ADMM, OSQP and other solvers handle this sort of thing?
I think
Like
they
you
just-
mentioned feasibility.
Yeah, they pretty much, I mean, and we had this issue with OSQP. So my understanding was that they were running a bunch of iterations and then doing this check on what they were converging to.
It's not,
like-
yeah, it's a little bit fancier than this.
Okay.
They're doing this thing called a homogeneous self-dual embedding.
Okay,
They're solving a different problem.
gotcha,
That's
okay.
like, a little bit fancier that lets them do this infeasibility detection stuff. And we don't want to do that because it's more expensive to solve. We
Yeah,
don't
yeah.
care about doing, but I think this like, looking into that a little bit might be worth,
Yeah,
yeah, I don't know, you just reminded me of this.
Okay.
Talk and I wanted to poke at it.
Yeah.
That's all good.
yeah, I had not, dived deep into that. I did notice that OSQP has some like infeasibility
Yeah. They'll give you,
checking
like,
stuff.
feasibility.
Certificate, yeah.
Yeah, which we can't do, but I don't
Yeah.
really care.
Yeah,
Can I just ask, expand on that question? Have you actually tried solving, infeasible QPs? I mean, or seeing how it handles those?
I don't think I have intentionally, and that would definitely be something I should try and see.
Because I'm wondering why the tools don't blow up.
That is a good question, because with the penalty offloading, they should,
Yeah,
yeah. They definitely should, and so it's maybe they do.
But the primers would show. Even if the.
Yeah, but no, yeah, the tools should blow up.
I mean, there are also like the sub-dual embedding, lots of tricks like that that will help you at least converge to something.
Gotcha.
yeah, I don't know, I just thought of it.
Yeah.
We hadn't looked at this at all, but I think it's something.
So that is something, yeah, to poke at, yeah.
Great, I'm done. Shall we open it up to the?
So is the matrix multiplier actually going to be linear or is it going to be something on the GPU?
On the GPU, the matrix vector, the multiplier,
Yeah,
should be linear.
like wouldn't you do all the element wise products? And like it's only the addition that's going to be.
Okay, I guess this actually speaks to how it parallelizes this across the course,
what-
because it
I-
could,
Yeah,
yeah.
that's how I would imagine if they would actually.
Yeah, so yeah, I don't know the details, and CUDA is very good, so it's possibly like what they're doing, you're right, it might be sublinear.
Because I think it is something.
But also these problems are so big. Like for example, you have 1500 variables and then the size of that weight matrix is like 3 times that, right? I don't know how many cores a GPU has, so I don't know whether it'll.
The ones we're using. are
I've
separate.
Yeah,
definitely
we just
observed that it's sublinear.
Okay.
I don't know, like I don't remember the number.
Yeah.
And the other question is, could you go back to the back solve? Like this-
Yeah. Oh wait, sorry, that's forward. Oops. Yes, guy.
Yeah, do you think like about those can be, like if you substitute in the equations for V3 and V2 and likewise, like so it will be an upper diagonal type matrix,
Yeah,
like you could do that in parallel.
yeah, I think you could,
How would
and
you
we should try
compare?
that.
What do you think?
I mean, it'll definitely, the terms will get bigger and bigger as you go. So I'm not sure what the actual operations look like, but yeah, and you'll do it twice. But thinking about that, like, if you compute that beforehand, that might also like be a linear.
This is-
So we should try
the
that.
values of B2, B3 to solve for B1.
Well, you mean V's, yeah. So I think what he's saying is if you take this equation and for V3 and like plug it in here and then like
Yeah, but then
expand it all out.
You need
B3 and part of-
B3 to solve for B2.
Yeah,
And so, like, you couldn't just put it out on the matrix there.
I guess like if you do the right multiply when multiplying the inverse with the D matrix, it will be like the upper triangular matrix multiplied by the B.
but that's, you're getting very close to doing an actual inverse there.
Yeah.
Like it has a
I
nice
see.
structure, but like, in
Like,
terms of the number of
would it end up
things,
being- Like I guess it's just.
I'm not sure.
I think it's gonna say,
Yeah,
like you basically pre-compute the inverses of the diagonal blocks.
Right.
yeah,
And then I think it's.
Yeah.
It's gonna be-
like it just says pre-computing the inverse. Yeah, yeah, actually, it should be, like
Yeah,
it almost
So
has to be,
Basically, it has to be.
like it has to
It should
be,
be.
yeah.
Yeah.
And like, I know there are tricks that you can do to get like, you know, order 2 to 2.7 or 2.6, but ultimately, it's gotta be. Any other questions?
I noticed that like on the speed up or the comparison of speed in some of those charts, there's a trend of like increased speed for larger problems. I'm just
Yes.
curious if you guys like looked into that.
Yeah, so there's a couple reasons we think that, so what you'd expect, right, is there's gonna be some kernel launch overhead. So the question was, you know, there's this kind of weird where you go up and then right before you start seeing the linear part, you go down in the speed. Part of it, we think there should be like some kernel launch overhead. So what you'd expect is you'd see like a flat curve and then you'd see a linear thing. In this case, because we're only solving for 10 problems and there's going to be lots of like 10 problems per, and there's lots of like CUDA issues, and you can see how big the error bars are, right? That's probably not like I don't know if that's a significant measurement. And so I'd be curious, maybe we should like run this for a lot more problems and see if we actually do see that, or if this is representing something in the GPU kernel launch that does have some problem scaling. I think if I remember, John also told me that there were some interesting like artifacts where once you got to certain problem sizes, like convergence rates. Oh, also, another thing is that because of checking convergence is expensive, we check every like 25 to 50 iterations. So that also affects like how big the error is pretty much, especially on small problems where you might converge very quickly, but you don't catch it until you've done 25 iterations. So that's probably where that comes from. I think it's mainly an artifact. Is there anyone on Zoom with questions?
That's a funny
There's something which.
Yeah, I definitely don't think that's something you can actually like. Plus, like, you know, OSQP beats you in that region for the most part anyway. So,
All right, if there's nothing else, I think we'll.
all right, well,
Call it.
thank you all for coming.
Thanks, everybody. And I